associate the dense ilmenite layer with creep and titanium marble directly in that sense. So in a dynamic model, it's an issue. In terms of the spread in ages, there is a big spread in ages, and there's a very serious question about what these ages are correct, whether they're ages of metamorphism, whether they're just simply bad ages. If you look at paranorthites to begin with, they're basically monomineralic rocks, plagioclase. It's hard to make, it's actually very easy to make a 1-point isochron. You get any age you want, of course. 2-point isochrons are subject to lots of uncertainty, particularly when they depend on the mineral plagioclase, which has a low closure temperature and is easily reset by shock. So for ferronorthites, there is this 100+ million year range in ages. There's some danger in the ages that exist from a 4.44 billion year age for 60025, like you showed, where we've now reproduced that, Lars will be talking about it later, and get agreeable lead and vanadium ages at 4.36. So I think there's some serious concern about whether this spread in ages is correct. I don't think there's a very strong argument, in fact, that the age of the moon, or that there is strong argument that the age of the moon is any older than, say, 4.45. And it might be, but there is no evidence suggesting that.
Really, really good points to remember that especially that geochemically the ilmenite layer and the creep layers need to remain discrete. All right, fantastic. I think that we've made it through our difficult period, and our next speaker is Ian Garrick-Bethel, his paper with Nimmo and Wieczorek.
Okay, thanks a lot. So the graphic on the left here is the moon during the magma ocean epoch, and on the right, it's Europa with its present-day liquid subsurface ocean, and hopefully by the end of the talk, you'll see that these may have something in common, these two different worlds. So the shape of the moon is of fundamental importance for understanding long wavelength, the geology and geophysics questions. You can see from these Lola topography data that basically there is an asymmetry between the two hemispheres, with the near side being lower in elevation than the far side, and the cause of this dichotomy is still under investigation. But today I want to look at this red bulge over here and focus on what that might be due to. This region here makes up a large part of the moon. It's known as the feldspathic highlands, and I would say because it makes up so much of the moon, it's important to understand its formation. And today I'm going to argue that this is not just a bulge of material, but actually has a lot of organized structure, and implies that it was due to crustal thickening and influenced by tidal heating. Briefly, the geology of this terrain, it's very low in iron. It's mapped by Jolliffe et al. And called the feldspathic highlands terrain. It's rich in anorthosite. More recently, it's been shown that this region has very pure anorthosite exposures with plagioclase, greater than 98% plagioclase in some locations throughout here and here. And that's consistent with this terrain being the primordial crust from the lunar magma ocean epoch. So different formation ideas for this interesting far side high topography. One is that a single large impact took place on the near side and removed the crust and just left the far side looking higher. We put some projector there. Another idea is that asymmetric crystallization processes in the magma ocean could have brought about higher crustal thickness and topography here. The hypothesis that motivated this talk is that this terrain, this bulgy looking terrain, is due to a frozen fossil tidal bulge. And by frozen tidal bulge, what do I mean? I mean at some point in the past, the moon was much hotter, and when it was, during this time, it was closer to the Earth. And when it was closer to the Earth, you had much higher tidal deformation. And if the moon cooled at that time, it could have locked in that higher tidal deformation as a frozen fossil bulge. So maybe this is what's left of that early epoch. Before we can look at any of these hypotheses, I think we need to quantify the structure of this terrain with our great new data set. So to quantify the structure of the terrain, I'll spend some time telling you how we did this. We started at the center of the feldspathic highlands, and we took great circle walks this way into the near side, and we took these walks on two different azimuths. And between that terrain, we average all of the data to make a nice swath. We do this averaging to remove the effects of small craters and other higher frequency effects that we're not interested in. Not only do we do that, though, we also fit those swaths walking into the near side to a cosine squared function. And a cosine squared function is what you'd expect from a tidal process, which is the hypothesis being explored. But not only do we do that, we also take the best fit function that we obtain from going in this direction, and we compare it to the terrain we encounter in the opposite direction, but don't perform any fits here. So essentially look in the opposite direction and see if our best fit function can predict the terrain in the other direction. If it can, then it's probably a good function to choose. Okay, so let's just look at an example of this process. We'll start here at the origin. This black dot here, and you can see great circle degrees of arc in topography being plotted. We walk into the near side and we fit the data to a cosine squared function. You can see that in this black area here. But then we also plot the best fit function over here and compare that with the observed terrain over here in the test area. For this example, you can see this function does a pretty good job of the fit function predicts the terrain for 90 degrees of great circle arc. That's pretty good. So you can also see I don't plot on the globe all of the data on this XY plot, but you can see that it doesn't really do a good job of predicting the terrain on the near side. We'll get to that later. But this example here does a really nice job with a cosine squared function. You can do this again. We use a diverse number of swaths to show how robust this is. You can see this also does this fits pretty well and predicts the terrain in the opposite direction for about 50 degrees of arc. Here's another fit over here, and this predicts the terrain in the opposite direction for another 90 degrees. So this 1 and 3 predict about 100. Cosine squared works for about 180 degrees, half the moon. So you can keep doing this. Just some more examples. And you can see all these functions in the fit area going into the near side do a really good job, some better than others. And it doesn't work so well when you get to the South Pole Aitken Basin. And none of them really work in the near side. And you can fit a bunch of other functions of equally free parameters, and you can see that these functions are less successful than a cosine squared function. Okay? So we can conclude, actually, that the function that describes much of this terrain is in fact cosine squared, and we can describe about a quarter, conservatively, of the lunar surface with this function. And secondly, this function terminates once you've gone about 30 degrees into the near side, so it doesn't work on the near side. Okay, and interestingly, we now have far side gravity data, and so we combine LOLA data and the new gravity data. We can get a new crustal thickness inversion, so there's kilometers of crustal thickness here. And we can look at this in the crustal thickness realm. So we can do the same exact swath, just a bunch of diverse swaths to capture the diversity of how well this works. And you can see for number 3 and number 1, you can predict lots of crustal thickness changes for 90 degrees, and you can describe a lot of the moon with this simple cosine squared function. Okay, so there's some interesting geology implications. Firstly, there's a continuity of this function between the far side highlands and the Procollarum creep terrain on the near side is very interesting on its own. These are two very different terrains. This one over here is very volcanic, radiogenic. Over here, it's very not volcanic. So that's interesting. We can also maybe use it to constrain the Procollarum impact basin, which may have caused all of that's one proposal at least, for the thick thinning of the crust here. Interestingly, this function is continuous across the proposed border of that basin, which suggests maybe that basin didn't actually form. So this is an interesting question that can be thought about more. But I want to also focus on what can actually cause nearly pure cosine squared or degree 2 crustal thickness variations. And it turns out that someone has already actually, about 20 years ago, worked out a process that can cause degree 2 crustal thickness variations for the satellite Europa. And so let's look at Europa. Europa is heated by tides from Jupiter, and in the ice shell that is decoupled from the mantle in Europa by a subsurface ocean, that heating is enhanced due to the larger deformations in that shell. Okay, so not only do we have heating in the shell, but furthermore, the tidal heating in the ice shell is spatially variable, such that it's higher at the poles and lower at the sub and anti-Jovian points, causing the crust to be thinner at the hotter poles and thicker at the sub and anti-Jovian points. So none of this is my idea. You can see here's a plot of the mean strain rate squared at the sub-Jovian point. You can see the heating will come to a minimum, and you'll get a thicker ice shell on Europa from Ojocongus and Stevenson. So now, maybe you see what I'm getting at. Like Europa, the moon once had a crust overlying a liquid ocean of rock, not of water. So what we did was we put together a model for tidal deformation due to earth tides and a floating anorthosite crust, and modeled this process using a bunch of things that are difficult to constrain precisely, but we did our best to be conservative and explore a few critical parameters. So we use a anorthosite flow law. We use a basal temperature of about 1200. We have to choose a semi-major axis and the eccentricity. So about 20 Earth radii we picked for the model I'm going to show. Eccentricity 0.02, about half what it is today, and a basal primordial heat flux. And although there's a lot of uncertainties, what I think is actually interesting is that for models where dissipation due to tides is sufficiently high, there's some striking similarities between the far side crust that you observe, and in the model. So you can see just right here these similarities. Okay. And we can actually just look at the same swaths as before. The wiggly lines are the actual crustal thickness. The smooth lines are the the model. And you can see it's actually not such a bad job at all, considering. So number 3 here is this. It does a pretty good job of the model versus observations. And if you look just in the middle here, you can see that there's some good agreement here and here. Even interestingly, this X terrain here is predicted to exist. That's right there and there. This is like a higher order effect that we may be able to explain with this model. Another way to do this is to look at spherical harmonics, and you can show that the dominantly degree 2 spherical harmonic power in the model and versus the dominantly degree 2 power in the observed crustal thickness pattern. Naturally, people ask, why don't you see this on the near side? I think, firstly, the near side is much younger and more thermally processed. And interestingly enough, it is possible that thermal evolution was much different, that volcanic evolution that precluded the development of this terrain here, or erased its signature altogether. Interestingly, you can take thorium from the near side, and it fits snugly into the region in crustal thickness, where crustal thickness starts to decay away from the cosine squared. So conclusions, this is an interesting observation that is described about a quarter of the moon, uniting two different interesting